Buenas noches. Good evening. Right, first of all, because of the my common sense versus your science thing, I've had to check notifications to see if anybody has put their hand up and said, yeah, we've got an explanation for you. It hasn't happened, obviously, but I haven't checked my Instagram for well over 3 weeks, maybe even a month, right? Just haven't been checking messages. So I had to go and have a look, and lots of likes, definitely hardly any abuse like there used to be. Because I used to feed that abuse by getting involved. So now I'm doing what everybody else does, just posting without any explanation. Seems to work for everybody else, doesn't it? Somebody did say, why have you got 2 dildos on the end of your pointer? When did that happen? It just so happens today we lay the pointer to rest. I've got a new one. Look at this. Awesome bit of machinery, okay? Now, my common sense versus your science. I stick with what I'm saying. Now today, it just comes out of nowhere. Have we heard of a megaphragma? Megaphragma. It's the opposite of a megalodon. You know, the big massive shark that swims and used to eat everything. Well, this little thing, so tiny, that horseradish is called. Now, we're going to have a look at this, and this is just a continuation. Don't forget something here. The solar eclipse, right? It is an indication of absolute light. Has there ever been a lesson dedicated to finite light and how it works with the solar eclipse? Why is it that it seems like the sun is directly behind the moon? Sweet spot, shadow, everything happening in real time. You'd think that it would be the perfect example, wouldn't it, of how to show how photons take 8 minutes and 20 seconds to reach Earth. Earth turns 2.08 degrees in that 8 minutes, 20 seconds. Surely it's the perfect situation. Everybody sees it. But, anybody who ever tried to explain the solar eclipse and trying to pass the light from the sun on as finite and traveling at 299,792,458 meters per second, anybody who tried to teach that lesson would hit a almighty speed bump along the way, because there is no way that this can be explained with finite light. A few of you have said, no, science explains it perfectly, but you failed to leave an explanation. The reason you failed to leave an explanation is because there is no explanation for 299,792,458 meters per second and the way a solar eclipse plays out. This is called common sense, right? From here, anything that steps over the line, science, magic, is horseradish. And it's taking you down a path of madness, right? Because it's all about people claiming knowledge that cannot be known. People. There are too many people taking the Mickey Mouse out of you. There are too many people making claims, claiming knowledge, and claiming achievements that cannot be achieved, knowledge that cannot be known, etc., etc. And you guys, you're taking it bait, hook, line, and sinker, because you're not thinking. You're just absorbing the idiocy that is being thrown at you. through TV screens, right? Now, we're going to go on a little journey. First, we're going to meet the mega fragma, okay? This just led me. My ears prick up when I hear an absurdity, see? And they prick up pretty fast. So, I did actually clean up. It might not look like it, but... So, let's... I'm going to try not to interrupt too much, but you know what? It annoys me that people believe this stuff. It's insane. Right, the strange physics of the super small. 2 days ago, about an hour and a bit ago, 2 hours, it was on 47,000. It's now on 50,000 views. So 50,000 of you are familiar with the mega fragma.
Insects have evolved extraordinary adaptations to navigate the world at scales we can barely imagine. Because when you're this small, the laws of physics have unexpected consequences. This is a type of wasp called megaphragma, one of the smallest flying insects in the world. It's just a few tenths of a millimeter long, some 5 or 10 times smaller than a flea. It has wings like paddles and flies in an unusual way. That's because air feels very different to it than it does to us. We're barely aware of the air around us as we move through it. And that's because of the science of air resistance.
Now, the science of air resistance, what is going to be thrown at you is fairly logical. A golf ball and a ping pong ball. Ping pong ball is really light. A golf ball, which I have, is heavy. So, but I do that with a ping pong ball, I can blow it away. That is the science of air resistance. But it doesn't end there. We delve into the quantum world.
Take a golf ball and a ping pong ball. It's easier to throw a golf ball than a ping pong ball. They both have the same surface area and so feel the same air resistance. But the ping pong ball is lighter, with less momentum, and struggles to push through the air. Megaphragma is like a tiny ping pong ball, with little momentum for its surface area. So to it, the air feels more like a liquid, and it's evolved its unusually shaped wings to swim through it. If you were to make this the size of a human, then it'd be barely able to move its wings, let alone use them to fly. Yet it's so successfully adapted to the world in which it exists that in recent years, entomologists have found them all over the world. Africa to the Pacific to South America, even in the woods outside London.
Even in the woods outside London. I was born in southeast London, Croydon of all places. There could have been megaphragmas outside the window, maybe even inside the hospital, in the room that I was born. Megaphragmas everywhere, shitting everywhere. Megaphragmas. Megaphragmas.
When we look at even tinier objects, 10 times smaller than megaphragma, we come to the scale of a typical animal cell. As we increase magnification...
Stop it there, right? Now, a megaphragma, how big? The 10th or 100th of a millimetre, all right? Now, a megaphragma. So don't try this at home, I'm a professional, okay? Now, how would the megaphragmas go there? Do we see that? Right, I'll do this off there so it's not politically incorrect. all the mega fragmas be up against that, wouldn't they? That mega fragma. Now, we head towards the 1986 Nobel. That's where I trace this back to. Right, so let's carry on. God. Look, this is old school science, okay? No, this is old school common sense. Now, after that, we're going to fast forward to 2210. It's all horseradish. The black paint that really, what did I say, 2210? So we'll go here. Now, the black paint, that is so black that it just absorbs all light, okay? Very clever. A few chemicals and that, and they made a really good black paint. That's kind of where it ends. But, damn. Okay. Oh.
Can you imagine the view from up there, Sarge?
With Budget Direct cover, I'd say it was nothing but blue skies.
Insurance solved with Budget Direct.
Not much we could do about the ads, unfortunately.
Foxtel's very big deal. Explore the world's best drama. Watch
There are too many people claiming knowledge that cannot be known. It's like climate change. To be able to call, predict, explain exactly why, if we're warming, you'd need to know about every single variable involved in the planet's climate, and nobody knows that. So that's where it ends. Anything after that, people claiming to know why we've heated up by 0.1 of a degree every year over the last 100 years, right? Because that's how much it is. It's 0.1 degree. No, 0.01 of a degree over 100 years is 1 degree. Carbon dioxide, man-made, horseradish. Nobody can call that. Knowing that, anything that comes after it is made up horseradish.
This card has been painted with the blackest commercially available paint. It's called Black 3.0. And yeah, it looks very black. But put it alongside the Vanta Black, and if I shine a light on them, you can see the paint just looks grey in comparison. And even more impressive, if I make an angle so that the light bounces off the surface and hopefully into the camera, you can see that this paint looks a lot brighter because the light has been reflected. But if I do the same thing with the Vanta Black, you should see no difference at all.
Hang on a minute.
All the light is being absorbed. None of it is.
I just noticed that. Look at the angles.
If I make an angle so that the light bounces off the surface and hopefully into the camera, you can see that this paint looks a lot brighter because the light has been reflected. But if I do the same thing with the Vanta Black, you should see no difference at all. All the light.
For the record, there was a slight brightness on it.
Is being absorbed. None of it is reflected. What is it useful for?
So its main uses are in satellite systems for controlling stray light from the sun, the moon and the earth when you're looking out at stars. It's also...
Now, looking out at stars, the light from the sun, the moon and earth, that light is absolute, right? So straight away, they're headed towards the stars and light.
to use for calibrating infrared cameras that look at the Earth for global warming studies. And
now they're using it to look at the Earth for global warming studies. Nobody anywhere has the knowledge required to be able to call why the climate is doing what it does. Nobody has that knowledge. To think that somebody does have that knowledge, you're kind of, your head, brain, everything is over the science magic line, because nobody knows what the climate's going to do tomorrow, and nobody knows why the climate does what it does. There are simply too many variables involved.
Terrestrially, it's used to protect cars with autonomous driving modes from sunlight entering the camera systems and causing ghosting and loss of signal.
Now, when has that ever been a problem? When has sunlight ever caused a loss of signal? I mean, it's the stuff that they say that nobody's really taken any notice of. It's horseradish, all of it.
For me, this is an entirely unexpected and surprising property of nanotubes. And more importantly, this is nanotechnology that we can...
And here we are again, right? Now, listen guys, this nanotechnology is where the divide starts, because they're so clever, aren't we? They are so clever, and everybody's in awe of it, aren't they? It's just unbelievable stuff, isn't it? Wakey, wakey.
See, or rather not see. Glimpsing tiny nanotubes was impressive, but could we go even further? By the 1980s, scientists were trying to see ever smaller things using a completely different approach. They wondered if they could see by feeling. Basically, the idea was to mimic the way the needle on an old record player works. A stylus passes along a groove on a record, and the tiny bumps vibrate the needle, making music. But of course, the tip of a record player stylus is far too big to feel something as small as an atom. But then in 1982, two scientists, Heinrich Rohrer and Gerd Binnig, had an ingenious idea. They put a thin metal spike into a corrosive liquid. Using electrical currents, they slowly dissolved away the tip of the spike so that just a very thin needle of metal remained. Its tip was just a few atoms in diameter.
Now,
Crazy tasty, we're the sweetest snack for you. Crazy tasty.
you did hear
Get smart. Replace your old water.
what was said. These two guys, Gerd Binning and Heinrich Rohrer, dissolved a metal spike, tiny metal spike or whatever, okay, and they dissolved it to the point. The point was an atom in diameter. Now, this right here, it's the robins, the European robins, using photons that hit the retinas, that then spin atoms, that then gives them some kind of magnetic navigation system. It's instinct. That's what gets them around, because Papa Bird, Mama Bird, Grandpapa Bird and Grandmama Bird, they've just been doing it forever. That's where they go when it gets cold. They go to where it's warm. Photons, atoms, quantum entanglement. If you cannot see what's happening.
Heater with a solar heart system and get up to a $1,000 trade-in.
Oh, come on with the ads. I might
You
have
can't stop a
to.
wave. It's all building to this.
This looks good.
point. You don't belong here anymore.
I just want to take my son surfing, mate. You have to know where the limitations are, and you don't.
But how could this needle see? One idea was to harness an unusual force of nature. This is a gecko. Its feet stick to the glass using a tiny attractive force called the van der Waals force.
Van der Waals force.
Van der Waals forces exist because of a rather quirky aspect of atoms and molecules. Think of an atom as a tiny positively charged nucleus surrounded by a cloud of negatively charged.
There are too many people claiming too much knowledge that simply cannot be known. It's gone too far.
Electrons.
But crucially, these electron clouds aren't static. They fluctuate in shape, often randomly. So the clouds can become lopsided with more electrons on one side than on the other.
Because opposite charges attract, the negative end of one molecule is pulled towards the positive end of another.
The force that an individual atom feels is, of course, minuscule.
I know. All this talk of stuff we cannot see. All these perfect explanations. An explanation for everything that exists. How about the sun and the moon and the solar eclipse? Do one of those, Jim. Do one of those. And just convince me, without hitting any speed bumps, that there are photons that are taking 8 minutes and 20 to reach us from the sun. It's so stupid, so ridiculous, and so oh, God, it hurts.
But these effects can add up.
And this in turn means that the molecules on the surface of an object can sometimes feel pulled towards the molecules on the surface of a nearby object.
And that's what the gecko is taking advantage of.
A gecko's feet are covered with billions of tiny structures called spatula.
Billions. Billions.
When these press against the glass, they flatten out, creating a huge surface area. Billions of atoms are now in contact. Then the tiny van der Waals forces combine and hold the gecko in place. And this was one of the forces Binnig and Rohrer believed they could harness.
When a tiny stylus, and remember its tip is just a few atoms wide, approaching
Its tip. Its tip is just a few atoms wide. Honestly.
atoms on the surface of the material, this is when the van der Waals forces come into play. Just like the spatula on the foot of a gecko feels an attractive force between it and the molecules on the surface of the glass, so the stylus feels a force pulling it towards or pushing it away from the atoms as it passes over the surface.
Measuring minuscule forces like these can paint a picture of the surface at the tiniest scale. This is a modern atomic force microscope. Dr. Georgina Ben is using it to understand one of our deadliest enemies.
I'm going to be imaging E. coli.
Now listen to what is being said. Don't just hear it, listen.
Which are a type of bacteria. So with a normal microscope, we could look at just the bacteria, but we need our atomic force microscope to be able to see the details on the surface.
Why are we looking at the surface of E. coli?
So E. coli are really good at resisting antibiotics because they have this extra protective layer around the outside. And we want to know how the protective layer is arranged so that we can help people design antibiotics that can get through the protective layer more efficiently.
So this is the full cell, the full bacteria.
Yeah. So you can sort of start to see features on the surface. And these are already well below optical microscopy kind of sizes. My scan's going to be 500 nanometers wide.
So we're now looking at the surface
Yes.
of bacteria.
Yes.
This is really impressive. What we're looking at here is bacteria skin, and it's, you know, you're looking at the craters and bumps and hills on the skin of bacteria to find these weak spots that we can attack with antibiotics.
Each one of these black spots is a hole on the bacteria, which is about 3 millionths of a millimetre wide.
Three millionths. This all went pear-shaped, guys, in 1971, when the atomic clocks were out by 300 billionths of a second. Or was it millions? Does it even matter? If you cannot see that science has long gone, the kids are in real trouble.
These are the holes that let water and nutrients in and out of the cell. So we're looking at how they're arranged relative to each other. And what's interesting is that
What does that mean? How they're arranged relative to each other. What?
got this really tight lattice of pores, and then sometimes there are these gaps in your lattice.
So those are the weak spots.
We don't know.
So
we want to know, that's like a next question, is why these are important, why they would be there in the first place. So we know that.
Why would they be there in the first place? If they are actually looking at something that's 3 millionths of a millimetre in diameter or whatever, working out why they're there.
Some kind of patches will make the membrane weaker, and some of them will not.
So if you could get the bacteria to mutate so that it generates these weak spots,
or
then
maybe
you can attack.
So he's telling her what she needs to be doing. Did you detect that? Let's play that again. She didn't tell him. He stepped in and told her that if she can make it, what did he say? Something. Listen.
important, why they would be there in the first place. So we know that some kind of patches will make the membrane weaker, and some of them will not.
So if you could get the bacteria to mutate so that it generates these weak spots,
or
then
maybe,
you can attack it.
Yes, or maybe get a drug that will make these weak spots, and then we could apply antibiotics.
Now, if you cannot see the bullshit, right, it would amaze me. It really would. Now where we're going to go is to the 1986 Nobel Prize winner. There's two of them, Gerd Binning and Heinrich Roher. Now, I looked in the books for these names, and they weren't in the normal world books or encyclopedias, all right? A couple of them. 1986, got a 1990, 1992. The names aren't there, but they are, loads of other names are in there, but they are in Science and the Future, right? They're in here, Nobel Prize winners. Now, you know what I think about Nobel Prize? People are winning Nobel Prizes for working out that the local universe is not real. Nobel Prize for working out that the local universe is not real. And there's a load of other ones. Now, go. So these are the people. This is one of the people who dissolved a metal pin, and he got the tip to be an atom in diameter. 1986. Red flag, red flag.
So, Heinrich Rohrer, welcome to Stockholm and to this interview with NobelPrize.org. You were awarded the 1986 Nobel Prize in Physics together with Ernst Ruska and Gerd Binnig for your joint work in developing microscopy. And in particular, you and Gerd Binnig received the prize for your design of the scanning tunneling microscope. Now, this is a device that enables us to look at the surface of objects at the atomic scale by means of a probe which skims over the surface and records variations in the topography below it with minute current fluctuations. What did this device enable us to see for the first time that we hadn't seen before?
As you say, surface structures in a different way. I mean, you had some ideas about certain surface structures, but you never saw it in, so to speak, in real space.
Mega fragments.
So you
Clear off.
It's just like if you would trace a surface with your finger, you see. So you see it in real space, and then of course, actually, you see the electrons on the surface. It's electronic wave functions, and so you also can see certain properties. You can see, you can test the hardness of a surface. But then, of course, in the same way, you also can take atoms. The principle is the same as if you take your fingers and you play around with small balls. And the fingers, if you take nano fingers, the small balls can be atoms. And it's exactly the same thing. You can take an atom, you can put it somewhere else, or you can take your fingers and glide over the surface and feel the surface, feel the bumps and so on. So with the same fingers, you can do two jobs. You can change it, or you can feel it.
You can detect it, or you can move it around. You can play with it.
Yes.
Right. And what, in those early days of using it, what were the first surprises that came up? Because as you said, you sort of had an idea, and then you could actually see. What surprises turned up?
Yeah, I think the first surprise was that we really could do it with atomic resolution, you see. Actually...
It must have been a big surprise. After dissolving a needle, a pinhead or something, down to the diameter of an atom, and then, well, the rest is history.
In fact, you can do it with atomic resolution. That's inherent in the approach we took. But we didn't expect it that we could make such fine fingers. But then every point of a needle ends up with one atom. And this very atom at the end, that's then your finger, you see. And this atom has the size of an atom.
Yes.
And so you can feel other atoms. That was a pleasant surprise that you could do it relatively easy.
I mean, on the subject of being able to do it, it seems unimaginably complex to make such a thing. That you have, because you're talking about atoms almost in contact with other atoms, there must be no vibration. You're talking about a probe which is, as you say, one atom thick at its tip. The mind boggles. How did you have the confidence to even imagine?
I like it. The mind boggles. Everything boggles.
That one could do such a thing, to make such an instrument.
Or let's say we didn't see any obstacle which could not be.
Why? Why would anybody see any obstacles when dissolving the end of a pinhead down to the diameter of an atom and then getting all of these readings? What was it? Why? Was it wired? maybe at the end superglued to the end of a copper wire.
Could not be overcome. And of course, there were quite a few fortuitous developments in the whole thing, but somehow luck was on our side. But I think you always, I mean, in science, you need luck, you see. And if you don't have the luck in a specific case, then you do something different. You might have luck in something else. You know? So that's, you see, it was less difficult, finally, than everybody thought. And that's why everybody thought you could not do it. And that's why nobody did it. And that's, I would say, a crucial thing in science. You see, everything is new because other people think you cannot do it. Or because other people do not appreciate that it could become important. And we live of novelty in science, so whenever you do something new, you have to overcome certain beliefs that it cannot be done, that it...
Basically what he's saying, if you have to overcome that thing called common sense. You have to overcome that. You know, thinking something isn't possible, because this was clearly possible. It wasn't that difficult to do. Just got to overcome.
It's not interesting answer.
So, I mean, it's interesting to ask why you and Gerbinner believed that you could do it, that other people were bounded by the limitations of what they thought they could do. You two felt that there were no obstacles, there was nothing insurmountable. You use a phrase in your autobiography that you wrote for when you received the Nobel Prize, that you'd lost your respect for angstroms. And that's a lovely phrase, an angstrom being 10 to the minus 10 meters.
Okay, I did in my PhD thesis, I did work where I worked, let's say, with angstrom dimensions, just mechanically.
So you weren't scared of the size?
And you see, this worked. And so...
he says the PhD thing, it's, I have to stress, right, astrophysicists, all these people, they have these PhDs. Where is the explanation for a solar eclipse and why the sun is directly behind the moon? Why? Why is that happening? Where is... It would be so good to hear a logical, finite light explanation for how the sun is directly behind the moon during an entire solar eclipse. Wherever the moon goes, the shadow hits Earth and the sun is directly, almost like it's absolute light, isn't it? So you've got all of these explanations for all this stuff that we cannot see, and it's very hard to believe, let's face it. But for the biggest things in our local solar system, where's the explanation? Where's the convincing explanation for light not being absolute? Because it obviously is. People, you need to understand where the science ends and where the magic line bullshit starts.
In principle, at that time, I knew you can measure angstroms, you see, mechanically, more or less mechanically. So why shouldn't you be able to do it in this way? And so,
No.
I mean, in retrospect, it's always easy.
Yes.
And, or let's put it this way, when I give lectures to the public, I always have a little bit of problem. I tell them, listen, if I explain you now what you...
Just reminds me, just a little bit. Have you ever played Nazi Knock Knock? It goes like this. So, don't mean to bring up part, it's just quite funny. So, knock knock, who's there? We didn't do the talking. Get it? So you played knock knock, but anyway.
We did in terms that you don't understand it. You go home and still wonder, what did these guys do? And if I explain it to you in terms that you understand it, then you ask yourself, what for something such simple you get the Nobel Prize, you see that?
And don't forget, ladies and gentlemen, we were winning Nobel Prizes for working out that the local universe is not real. Okay? Don't forget that.
In any case, it worked out nicely.
Yes, indeed. There's another phrase you use. You talk about the light-heartedness of your approach, that you approach things with perhaps less seriousness. I don't know, maybe that's not the right word. There was less it was less momentous to do what you were doing than other people might have felt it was about to be.
Yes. Okay, I think both Gerd Binning and Ivy are not...
It's just, I didn't watch much of it. I mean, it's obviously horseradish, isn't it? Let's see what happens here.
Him. And then I think in many cases he was the technical crucial figure in the whole...
I obviously missed a little bit. I just want to hear him talk about the good stuff.
And there he has to perform. So getting out into something else might not be necessarily more difficult, you see.
Whatever the case, it's obviously a very fortunate circumstance that you found yourself within IBM, where they would allow you to make such jumps. Presumably you didn't have to go through a sort of grant proposal type.
They were happy.
Yeah, they encouraged it. Yes.
Okay, they were happy that I did something else, not because I was not performing in that thing, but
he did well, didn't he? Dissolving a needle, a pin, into something with the diameter of an atom. Wow.
It was the macro scale to, let's say, down to the micrometer as a precision scale. Mm-hmm. And then came the IT revolution, the information technology revolution. That was in the scale of micrometer. And so, but you see, it wasn't the micro...
We could go on all night, right? Couldn't we? I guarantee you that there are a lot of people claiming knowledge that simply cannot be known. They've bamboozled with claims in 1971 of two atomic clocks, east and west, flown around the planet, and there was some atomic clock they were synced into in a US naval base. I think it was in Virginia or somewhere. And when they got back, they were out of sync by 300 and something billionths of a second. Now, this is science magic. We've skipped over, and since then, bye-bye tardigrade. That's another level, isn't it? Tardigrades. They find them on the moon, in space, clinging to the wings of the friggin' spaceships. There are people claiming knowledge that cannot be known. It's so obvious. It hurts. Wake up, people. Start thinking. Asking questions instead of accepting everything. The kids are going to pay for it. Laters.